So what we're going to do is we're going to take a look at the next topics in magnetism, which is going to be looking at the Biot-Savart law is our next stop. So here, let me kind of share screen here with you and take a look. Here I am in the unit packet. You can see here's the outline for the magnetism unit. We have already done the introduction to magnetic fields, talked about magnetic fields are and how we draw magnetic fields, talked about the way that magnetic fields, they go out the north pole of a magnet and the south pole of a magnet, talked about Earth's magnetic field, talked about Gauss's law for magnetic fields and how if you have a closed surface, because magnetic field lines always make complete loops, if you have a closed surface, field lines, any field line going in, because it makes a complete loop, will at some point come back out of that surface to make its loop. And so you will now always have a total flux of zero. Remember, flux out of a surface is positive and in is negative. The total flux will be zero for magnetic field. So frankly, we don't really use Gauss's law for magnetism for anything other than to point out you can't just have a point called a pole, a monopole, where magnetic fields are radiating out from. It doesn't work that way because they make complete loops. So anyway, so it's different than electric fields in that sense. Moving on, part B. It says looking at the interaction of charges with magnetic fields. So we talked about the fact that if I've got a moving charge, it gets pushed if it cuts across magnetic field lines. And so we call that force the Lorentz force. And it involves doing a cross product, right? That magnetic force being Q V cross B, the charge size times the cross product of the velocity of the charge and the magnetic field strength. And so there's a sine theta hiding there in that cross product. And so we care about the angle between the direction of the charge's motion and the direction of the magnetic fields. The direction of a cross product is given by the right-hand rule. And so being able to do that V cross into B to give you your force is key. Anyway, and then we talked about the fact that, well, gosh, if charges cutting across field lines get pushed, what if those charges that are moving across the magnetic field lines, what if they're moving across because they're flowing down a wire, right? You have current in a wire that crosses field lines. You say, well, those charges should get pushed. Well, because they're not going to just jump out of the wire, the whole wire gets pushed. And so that force on a current carrying wire, it's something we can calculate. We derived the formula for that using our formula from looking at the microscopic model of current, of looking at current in a wire and turning it into an equation in terms of the motion of the individual charged particles. That's that on the AP formula sheet, that's I is NeV A, where that's charge carriers per volume times the charge of one of those electrons, that's the little e, times the drift velocity of them down the wire, times the cross-sectional area of the wire. Anyway, if we combine that with the QV cross B, we can get that formula for the force on a current carrying wire, which is IL cross B. And again, we invented a little vector, that L vector, length vector that goes along the wire in the direction of the current. Anyway, so you have to do a cross product with that to get the force on the wire. Okay, moving onward. I'm sorry, I've spent too long reviewing old stuff. Anyway, once we did that, we said, hey, you know what? If I have that wire and I bend it around into a loop, right? And I go ahead and I insert that loop that I'm running my current through, and I insert it into a magnetic field, right? Say B field line's going to the right here. Then you say, well, gosh, if the current's coming in this way, the field's going right, V cross B forces down. This side will get tugged down, and on the opposite side will get tugged up. That will make this whole thing want to rotate. And we said, hey, that's going to be the start of how we make an electric motor, okay? And so we said we need to be able to calculate that torque, and we figured out how to do that just using the torque equation. For torque is R cross F, and combining that for the F in that's that magnetic force, IL cross B. We said, hey, remember there's a torque on each side, so I got to double it to get the total torque. When we did that, we came up with an equation for the torque on a current loop. That equation is not on the AP formula sheet. It's something you need to be able to derive for the case that they're showing you. But it ends up being like N for the number of coils, number of times we loop around in our coil, times the current I, times the area vector, which is just the area, it's a vector that sticks straight out, crossed with the B field. So NIA cross B. And we came up with that. Again, that's not one that you would have memorized. It's something that you would derive. But anyway, the idea there, being able to calculate that twisting force, that torque, it's kind of cool, okay? And it's going to be a function of what angle this thing has rotated through, right? So we'll get more torque, maximum torque when it's oriented like so compared to the B field, and zero torque when it's oriented like this to the B field. Okay, anyway, moving onward. And that was kind of that section. Oh, we talked about mass spectrometers, right? Which are these super cool devices for figuring out like what materials a substance is made out of, right? You heat it up, to a plasma, so you like ionize the atoms. So you have these individual ions, and those positive ions then are directed through crossed electric and magnetic fields, right? And because you have those crossed fields, the magnetic field tries to tug the charges one way, and the electric field tries to tug them the other way. And when those forces balance, it'll just go straight, and then it'll go through this other little hole. Then only the ones going at just the right speed will that magnetic force be big enough to balance out the electric force. And then they'll just go through the two holes, and so now you have a beam of particles that you know the speed of, and that's enough for you to figure out if they go into an area that just has the magnetic field, the radius of curvature, and from where they hit, then you can figure out what that ion must have been. And then we derived the formula for that radius of the curve that charged particle makes in a magnetic field, right? And that is, again, something you would derive. It's not something you would memorize for the AP formula sheet, but that ended up being what? The radius was, wasn't it M over Q, which is that mass to charge ratio, times the ratio, I want to say E over B? I think that's right. No. Because that was the speed, right? The speed was, no. Yeah, I think that's what it comes out to be. Anyway, like I said, I would derive it again from scratch. I wouldn't try to memorize that. But the point is that it's a charge to mass ratio, or mass to charge ratio that's involved there, determining that radius of the turn and the mass to charge ratio. Every isotope, every ion on the periodic table has a different mass to charge ratio. And so, yeah. Yes. Okay, and so that lets you identify what it is. By that radius, the turn it makes, where it hits in the detector. Okay, good enough. Where are we going from here? The next thing we talked about was the fact that if you run current down a wire, it makes a magnetic field around the wire. It turns out anytime you want to make a magnetic field, you have moving electric charge is how you make a magnetic field. And so we said, well, gosh, we started with just if I run current down a long straight wire, what does that field look like? And we went ahead and figured that out, that it makes these loops around the wire. You say, hey, which direction does the loop go around the wire? And we said, well, we need another right-hand rule to figure that out. Okay. And so we said, hey, I'm going to take this wire. I see the current's going to the right. I would grab the wire with my right hand. Okay, not the left, because remember they're chiral. They're mirror images of each other. So I take the right hand, grab the wire with my thumb pointing in the direction the current's going. So the current's going to the right. I grab it like this with my thumb pointing to the right. And then the way my fingers, my right hand naturally curl around the wire is the way the magnetic field lines loop around the wire. If I were to use the incorrect hand, I would get the opposite direction for the curl. See, with my left hand? See, that's not cool. So you got to always, like if you're a righty like me, you got to drop the thing you're writing with when you do the right hand rule to test it. So some people, they're busy writing with their right hand and they try to use their left hand to do the right hand rule and get the thing backwards. Okay, but anyway, so we talked about what if I took the wire and I bent it in a loop, and we realized that the field made by each little bit of the wire, they'd all overlap in the middle, make a really strong field to the middle of the loop. And so we said, gosh, if I want to make it really strong, I'll just take my wire and I'll loop it around and around and around and around and make a really strong field that shoots down the coil. Alrighty. Anyway, and a shape like this is called a solenoid. Okay. Well, the shape is called a helix. It's a helical winding of wire. But the name for this device, where I have a wire and a spiral that I run current through, it's called a solenoid. Usually, we don't put empty space in the middle. Usually, we put some material in there, like some material that's a magnetic type material, like iron, like an iron bar or something. We put in the middle and wrap the wire around, and that's how we make a powerful electromagnet. And I think that's just about where I let up. Okay, last time I went ahead and I also showed you just in passing, I just kind of put on the board at the end, hey, this is the equation for the magnetic field made by a long straight wire that has current flowing through it. I mean, I showed you that formula. It was like B is mu naught I over 2 pi r. But what I want to do today, finally, getting to the point, is I want to go ahead and figure out how do we calculate magnetic fields. I want to find the magnetic field strength for, say I got current going down a wire, and I want to figure out how strong the B field is some distance away from the wire, right? How do you calculate that? And it turns out there's two techniques. One's called the Biot-Savart law, and one's called Ampere's law, right? And if I take a look here, I can see that in fact is the next thing here, how to create a magnetic field. We talked about diagramming magnetic field some, calculating magnetic field strength using Biot-Savart and Ampere's. That's what we're doing here, okay? So that is the goal.